Hi there, and welcome to this video about topology optimization in Hyperworks X. We're using today a two-dimensional example of a cantilever beam, and yeah, we're using the geometric built-in functions of Hyperworks X using the new workflow. It will be pretty awesome, so stick with me here. Now, first of all, let's talk about the model. So what is it what we are going to do today? So we have a cantilever beam, but in this case, oh, I'm sorry, that's the wrong color. In this case, it's just a plate. And we have it fixed here. And we have a force applied here. And we'll see about what's coming out from the topology optimization. If we say that this is the design space, and let's say we have 300 millimeters of height and 900 millimeters of width, and let's say we have, what could we do, 50 millimeters, 20 millimeters, yeah, let's say the thickness is 20 millimeters. So this is the geometric properties defined for our plate, and we will not include or exclude anything out from the design space, so completely free design space. The force is located in the middle, so that's important to know. So this is 150, and the 300 are this one. And yeah, I think we have steel as a design material. And without further ado, let's get into the modeling. So I will follow the same phases as with the 1D example. Just quickly write them. We have first is the data phase, where we have material property component. Then we have geometry and mesh. And finally we have analysis, where we have loads, boundary conditions, and the load step. Finally, I will check them off as we go through it. So, first things first, create a material. So, those are model properties. So, material here, that's steel. We'll check mat1. As a reminder, be in the OptiStruct profile. If not, file, solver profile, and then OptiStruct, because we are using OptiStruct throughout this course. So name is steel. The Young's module is 210,000. Poisson ratio is 0.3. And don't forget to set the density, because the density is used to calculate the mass of the topology optimization result. So better set it. Okay, that's it for first thing. Already check it. Wrong color. Material set. Second thing is the property. Properties. That's a P-shell property. So material is steel, and the thickness, what did we say, is 20 millimeters. So set 20 here. That's about it here. Another thing checked. Oh, that's not what I wanted to do. Okay. So that's checked, and now we are going to model the components. So right click here, create component, and in this case, this is my plate. So assigning the property, and material is assigned automatically. Another thing to check off the list. Now, we have the geometry. So we go into the geometry ribbon, and now we can say we have, first of all, we create a point at 0, 0, 0. That's always a good idea. And next thing, we want to create a surface. And here it's important that you have the right alignment, right? So this is wrong, but X should be pointing to the right, Y, what's arbitrary, could be set either way. But it should be an orthogonal plane. So X, Y, Z should be okay here. And then we just create a rectangle. So, zack. And the width is 900 and length, oh, yeah, is that correct? Yeah. Seems good to me. 900, 300, right click, left click, left click. Okay, so we created our first, that's not really a plane. So for that to be a surface, we have to click on surfaces and just select all lines and hit OK. See that there's a little check mark here. Watch out for it and then click here left. That's it. So we can now right click and leave the menu and maybe get a little bit dark color. So next thing is meshing. In this case, we do it just auto mesh with F12, but you also could do that with mesh and then general 2D mesh and then, well, panel mesh. That's also possible, but I'm used to do it with the F12. So selecting surface, 10 millimeters, maybe too little, maybe 5. Yeah, 5 is good. 5 is good. Just thinking about how long it will take for the optimization. Return it, and now if you want to check if the property has been assigned correctly, then you could just go into property, into element visualization, check the shell thickness to on, and now you can see it's on. So we are, the element size is too small because it's, from the thickness point of view, it's much too thick for this element size. But for topology optimization, it's not that big of a deal. We can use it right as it is right now. And yeah. Now, we have checked some things from our list. So geometry is done. Mesh is done. Next thing is analyzes. So analyzes, we create load collectors first. Load collectors for the loads. And leave the panel here. And, well, what did I forget? What I didn't do is I didn't split it, the plate in the middle. It's not big of a deal because I have the middle here and there is a line in here, but should have done that before. I will just quickly do that, geometry and then to split and then right click here. So it should snap on the midpoint. Rather, yeah, snap to the midpoint. If you have your mesh here, it will snap to every mesh point. But I want to do the geometric point, in this case mid, that's okay. And that's also okay, and then split. Now yeah, the elements are still here. And so it's perfect. Because I now can select this node here and be sure that's in the middle. If I have a mesh size which would put a node in the middle, then I would have to do the meshing all over again. But it's okay in this case. So loads. In this case, loads is color red. And I will just create a load here. So it's in analysis, then a single force. What did I say for the load? Didn't define it, right? There's an arrow, but no amount. Let's stick with 300 newtons. I'm not quite sure how much is appropriate here, but let's stick with 300. It's better to get a little bit below the limit as the opposite. Okay, so selecting the load, in this case it's this one right here. Why is it not selected? Okay, that's strange. I deselect it again and select just the one here, that's okay. And then we have -300 and the direction is y-axis. So it's pointing downwards. Create it, and as the next step, we want to do our fixed boundary condition. So create another load collector, SPCs, and hit the boundary condition, constraints. And for that reason, there's multiple ways how to select all the points on the left side of this cantilever beam. One would be to just align it and then simply do a rectangle. But you see, it's a little bit different or a little bit difficult to select it here. So that would be one way. The other way would be just hitting the yellow sign nodes and then say here by geoms, and then lines, and then this line and that line, and add to selection, and you're done. All DOFs selected, that's a good idea for this case. So it's fixed in all directions. And you see the colors matching. So that's also good. And as a last thing, I want to set up a load step. Load step, LS1, SPCs, SPCs, loads, loads. So that's okay. Linear static is also okay, and created. Now we have a load step here. So that's all about it for our analysis. And what I didn't do here, I didn't set up what we have to do for the topology optimization. Ooh. So we have another few phases, I would say. The first phase for the optimization is defining all the responses. And the other phase is defining design constraints. And defining the optimization objective. And what I did forget here, well, we just don't have to put only the responses, but also the optimization design variable. So des var. Actually, we are starting with the des var. So getting back to our model, maybe let's first run a quick analysis to see if the forces are off or if the model is set up properly. So I save it as a hypermesh model, and it's in this case plate 2D analysis, and we just run it with the run button on the analysis symbol and just hit optistruct. I don't think this will take that long, maybe 10 seconds. Yeah. So the displacement is rather small, everything fine, we can work with that. Now, creating the optimization. We are all in this panel, it's a ribbon, in the ribbon optimize, and you could see there's a lot of different optimization options. For example, a topology optimization, topography, size, shape, God, whatever you want. For us, it's topology. So topology. And you see that a topology design variable is created right as you click it. So you call it, for example, my des var. And you also can see that in the Model Explorer, you have, or Model Browser, you see that you have a design variable here. That's what you're creating right now. Keep in mind that they have to match. So the design variable property type has to match a property which is selected now. We have just one property, but this property is of type shell. So don't ever put here something different than p shell if you have a p shell property. Now you can assign different options here, but we are sticking with the defaults here. Even if it's not the best or the optimal solution right now, we could use symmetry constraints, we could use minimum member size, maximum member size, etc., etc., etc. But that's for another time. This video is just about the basic topology optimization. So p shell property set, that's it, close it. And now it's the thing that is common in every default topology optimization. It's the same thing more or less. You create responses. So first of all, let's check. We have our des var. That's the wrong color. I don't know why it's switching. So des var is set. Responses are next. Responses are set up in the same ribbon, optimize. I click once on responses, and that's creating, just this click is creating a response. So in this case, we want to create a response compliance. Compliance is the opposite of stiffness. Yeah, stiffness. And we want to minimize our compliance. That means maximizing our stiffness. So compliance is a name, but it's also has to be set in a response type. It's not a big of a deal if you're if you're just calling it compliance and it's a response type mass. So setting that to compliance. That's the first thing. Second thing is we want to have a volumefrac. Volumefrac is the fraction of the optimized volume divided by the initial volume. So it's between 0 and 1. So if it's 1, all the material which is initially there is used, and if it's 0, nothing is there. So it's a fraction. If the solver uses just half of the material, so it saves 50%, then the volumefrac would be 0.5. And we use that. So that's the responses which we wanted to set. And now we have the design constraints and the objective. Maybe I will point that out right here. The design constraint is that the volumefrac is below, for example, 0.1, which means that 90% of the material has to be removed. Fraction has to be below 0.1. And the objective is a minimization of compliance, which is the same as saying that the design has to be as stiff as possible, but with 10% of the material, as stated in the design constraint. Now, constraints are set here. I'll click here, and I want to create this as volumefrac 01 constraint. And the load step is not important, I guess. The response is volumefrac, and we have an upper bound of 0.1. So it has to be below. That's what we call an upper bound. If it has to be above, that would be a lower bound, which also can be used, but not for the volumefrac, I guess. Okay. Finally, the objective. Hitting once here objective, that's my objective. And we have to minimize the response compliance. And here it asks you for a load step. So we have to give it a load step we have. In this case, just one, so it's rather simple. If you have multiple load steps, then you would have to use weighted compliance, which sums the compliances of the different load steps together and minimizes this objective. All right, that's about it. So we are saving that as a model. Play to the, and we call it optimization. And it's good practice if you run it here to just put the volumefrac 01 at the end of the model, because then you know what, maybe you want to change the volumefrac upper bound constraint later on, and then you can do multiple runs and just changing the name here. And I hit optistruct, and now I'm not quite sure how long this takes, maybe a few minutes. Could be, yeah, a few minutes. I will speed up the time. It's done, but it's not quite done because it said limits and iterations reached. If you want to increase this limit, then you could do just optimization, opti-control, and then you have the def max, which you could set to 100. And then just go it one more time. But we can also do a restart, I guess. Let's see. Because I want to continue where it left off. That's why. And what you also can do is you could look at the graph. So look at what the compliance is doing. So it's decreasing, it's decreasing. That's good. We want that to decrease. Finally showing some convergence here. I think I'll speed up. Oh, no, never mind. It's finished. And now this is what you want to see. Optimization has converged. So you have a feasible design, all constraints satisfied. You can look at the graph. You can see it decreasing. See there's different functions here. But you're interested in the design. So you click on results. And this opens two files in Hyperview. First file is the underscore des.h3d, which is this file here. This gives you the contour of the design result. So clicking here, the last iteration, you see, oh, we got a lot of annoying checkerboard. It's called checkerboard. It's like checkerboard, whatever. You see that you have a lower density and a little bit higher density, and that's changing all the time. So what you can see here is that the volumefrac is maybe a little bit too low because you have just this little small design to here, and yeah, so you should increase that. And yeah, the second file which is created is the S1 or sx.h3d file, which is a load case, and there you can see the displacement of the initial design and also the last design. But in this case, it's not really the last design because it's opening the first one we calculated, but we did a restart, which we could access here. So yeah, but as we also would have to need to increase the volumefrac constraint and run it again, let's give it a try one more time. So we have our volume optimization constraint. You see here upper bound, and in this case maybe upper bound 0.3. And in this case we're changing the name here and run it again. But yeah, we're doing it in this case like that. And I'm speeding up the time and get something to drink. Oh my god, something did not work here? Restart. Oh yeah, there's another restart here. Sure, so skip that. I'm fetching something to. Alright, looks good. So you can see our graph. So it decreased the compliance accordingly. And optimization converge, feasible designs. That's good. So click on results, opening those two files again. And checking the density contour once again. Yeah, you have the checkerboard effect still. You can get rid of it with different kind of methods. We'll just quickly point that out to you. So optimization, opti-controls, there's checkerboard effect, decreaser or influencer. If you change that to 1, that's one thing. But it's not recommended, I guess, not so much. The other one is discrete, to set that to 2. In this case, for shell elements, because shell, this value +1 is the penalty factor, in this case 3, and 3 is the recommended value for shell elements. If you had solid elements, then discrete 1 would be good. And finally, what you also can do is changing the parameters in the design variable, which are the minimum member size and maximum member size. We had a, let me just quickly look at what the element size was. So distance panel 5. So let's say we have a minimum member size of 15 and a maximum member size of 40. Now the checkerboard effect should go away. Min member and discrete 2. Just check it once more. Well, how long did it take? Well, it's not that big of a model, right? What was the iteration count? 39. That's okay. In the meantime, we could look at different files in here. So just navigating quickly to that cantilever beam. So what's really created here are some different files for each iteration. So they are updated, but I want to point out a few of them. So there's S1. Those are the two which are opened after the optimization. And then we have also the out file, which is basically the thing which is here, but a little bit more. So see that information about the different values of each iteration. So also the discreteness you could see here. So 85% had a density between 0 and 0.1, and we have 2% here, and we have a little bit of of middle density and elements, and you can see that changing. It should disappear or become less and less and less, which is the case. And also the thing with the mass, yeah. Remember that I told you that you have to set the density, and this is why, because now you have mass values in the out file for each iteration, which is pretty cool to get. And what else? The compliance, which is the objective value, so it's also plotted for each iteration, and you see that here. It's the same thing as going through the graphs, and we're done already. So 56 iterations, and it converged successfully. Now I'm pretty sure, or I'm hoping that the checkerboard is not present anymore. Well, it's not present anymore. We will still have some things to sort out here. Maybe increase the maximum member size a little bit, or play with the volumefrac values. But there's also different ways of looking at it. You could also do an ISO contour here, which just shutting off the lower density elements. And you could also export it and build it with your favorite CAD tool, for example. So this concludes this video. If you have any questions or remarks or something you wanted to tell me, leave a comment. I will get back to you soon. And thanks for watching. I hope to see you next time.